So back in the 1028 material, we set up an integral, a triple integral, corresponding to the region bounded by a hemisphere and by a plane. And then in the concept check for that material, you set up the triple integral for the region bounded by a cone and a hemisphere. Now, we only set those equations up. We did not evaluate those integrals, unlike the nice integral over the cube that you were given in the 1029 concept check. And the region that we were dealing with there really had a circle-ish nature to it. The region of integration in both cases, where the top surface and the bottom surface intersected each other, that region was in the shape of a disk. And so Cartesian coordinates are really not appropriate for integrating over disc-shaped regions like that because the limits of integration are so complicated. So in the last section of chapter 12, we're going to be talking about using the other coordinate systems for 3 dimensions to make problems like that a little bit easier. And today we're going to focus on cylindrical coordinates. So we're going to review what cylindrical coordinates are and how they can be used to describe regions. And then we're going to talk about how we can convert a triple integral into an iterated triple integral using cylindrical coordinates. So let's go ahead and get started. Now, the formulas for cylindrical coordinates are very nice because it's basically just polar coordinates with a z on top. So we have r and theta representing in the xy plane exactly the same thing that they did in the world of polar. And then we have the z coordinate, which means the same thing in cylindrical that it does in Cartesian. It represents a vertical displacement. Now, with that said, let's just jump right into it. Let D be a 3-dimensional region, and suppose that the region D is bounded below by the surface z function of g of xy, and above by the surface z function h of xy. And suppose that the projection of D, when you look at the shadow on the xy plane, suppose that that region can be described in polar coordinates. On the outside, r is a function of theta. On the inside, r is a function of theta. And theta goes between these two angles, alpha and beta. So if you're in the position where you have a top surface and a bottom surface, z as a function of x and y, and then the shadow on the xy plane looks like something you can easily describe using polar coordinates, you can set up your iterated triple integral using cylindrical coordinates dz, dr, d theta. Z is going to go between the bottom surface and the top surface, where we have g on the bottom and h on the top. But instead of using x and y, since this is in cylindrical coordinates, we're going to use their equivalents, r cosine theta and r sine theta. And likewise for the bottom limit, r cosine theta, r sine theta. The r limits stretch between the lower function of theta, the bottommost function, so on the inside, f2 of theta, f1 of theta, and theta itself stretches between the angles alpha and beta. Now our integrand as well, we can't write f of x, y, z, because the coordinates x and y don't appear in polar or cylindrical coordinates. So instead we go through and we replace every x by an r cosine theta and an r sine theta. But z gets to stay. And finally, just as in polar coordinates, if we're using cylindrical to write a triple integral, we have an extra added factor of r. So, lower upper surface, inner outer radius, first to last angle, integrand in polar coordinates, and an extra copy of r. Let's see what that process looks like in the following example. So let D be the region between the cone z equals the square root of x squared plus y squared, and the plane z equals 2. Let's integrate the function f of xyz equals 1/2 x plus z over d. So let's start by getting a sketch of the region D. Now, as always, if you're not familiar with what the graphs of these functions look like, if you haven't memorized that, then you can use technology such as GeoGebra to obtain those graphs. But I know what they look like. The cone looks like a cone with its vertex at the point 0, 0. And then the plane z equals 2 comes out on top. And they intersect in this circle shape. Okay, so let's try and set up some cylindrical limits of integration corresponding to this 3D region trapped between the plane in orange and the cone in cyan. Alright, now the lowermost surface is the cone on the bottom. So let's rewrite this in polar by replacing x squared plus y squared with r squared. Z equals r is the equation of the cone in cylindrical coordinates. And on the top we have the plane z equals 2. Z equals 2. And since z is in cylindrical coordinates and 2 is just a constant, this equation doesn't need to be converted or modified at all. Z equals 2 is on the top. Alright, so now that we have established the top and bottom limits, let's go ahead and let's look at the shadow of our region D on the xy plane. And let's try and describe that using polar coordinates, r and theta. Let's extract that picture. And we have a disk of radius something. Now I've jumped to the gun a little bit and I've said that this disk has radius 2. And my hint is that this disk, its outer rim, corresponds to the outer limits of this space where the plane and the cone meet each other. So here's the plane, here is the cone, and if we set the equations of the plane and the cone equal to each other, plane and cone intersect at the point where r, this half of the equation, is equal to 2, this half of the equation. So that tells us directly that the radius must be 2 for this disk. So the allowed radii of points in this disk can stretch from 0 all the way to 2, and theta can go from 0 all the way to 2 pi. So for our limits of integration, we found that z equals r, that cone is on the bottom, z equals r. Z equals 2, that plane is on the top. The r limits of integration stretch from 0 to 2, and the theta limits of integration stretch from 0 to 2 pi. Okay, I probably should have left myself some more space here. Let's do dz, dr, d theta all the way over here, because the time has come now to consider not just my limits of integration, but also my integrand. So I'm integrating the function f of xyz equals 1/2 x plus z. Now the coordinate x is not permitted in cylindrical coordinates, so I'm going to have to replace x with its cylindrical equivalent, r cosine theta. But z is just fine in cylindrical coordinates, so it gets to stay put. Now something is missing from what I have written here, and that of course is the extra factor of r that we have to include anytime we're doing either cylindrical or polar integration. Cylindrical for 3D, polar for 2D. So let's distribute that, and let's go through the process of actually calculating the value of this triple integrated integral. 2 pi, and we have 1/2 r squared cos theta plus z r after distributing. Now that we have distributed, let's go ahead and integrate that. I'm going to work separately on the inner, middle, and outer integrals, focusing first on the inner layer. And we have 1/2 r squared cosine theta times z, treating both r and theta as constants. And then applying the power rule, we have z squared over 2r, evaluated as z goes from r on the bottom to 2 on the top. So plugging in z equals 2, we now have 2 times 1/2 r squared cosine theta. Z equals 2, we now have 2r. Z equals r, we now have r cubed over 2 cosine theta. Z equals r, we now have z cubed over 2. R cubed over 2. Of course, by the time we finish our dz integral, all instances of the letter z should be gone. Okay, so next let's do the middle integral, where we're integrating going from 0 to 2, our integrand, plus 2r minus r cubed over 2 cos theta minus r cubed over 2, integrating that with respect to r. So applying the power rule, we have the integral from, we have r cubed over 3 cosine theta plus r squared minus r to the 4th power over 8 cosine theta minus r to the 4th power over 8, evaluated from 0 to 2. Plugging in r equals 2 gives us 8/3 cosine theta. R equals 2 gives us 4. R equals 2 gives us 16 over 8, which is 2 cosine theta. Then 16 over 8, 2. And plugging in r equals 2 will cause all 4 of these terms to vanish. And finally, we've made our way to the inner integral, where we have the integral from 0 to 2 pi of the result of the previous step, cosine theta, plus 4 minus 2, so I'll just go ahead and combine that to plus 2, minus 2 cos theta. I suppose I could even combine these cosine terms. 8/3 minus 2, 8/3 minus 6/3 would be 2/3. So I'm just simplifying a little bit more. Alright, and now integrating these two terms, we have 2/3 sine theta plus 2 theta, evaluated from 0 to 2 pi. And finally, plugging those in, sine of 2 pi is 0, sine of 0 is 0, and so we get 2 times 2 pi, and plugging 0 in for theta will make that 0 as well, and the result is 4 pi. Alright, so that is an example of setting up and calculating a triple integral in cylindrical coordinates. Sort of a fusion between the work that we have done, setting up triple integrals in Cartesian coordinates, and the work that we have done setting up polar integrals for double coordinates. Tomorrow we'll talk about the case that our region is more conducive to the use of spherical coordinates, rho, theta, and phi.